Okay, welcome. Hello, everybody. Welcome to the third Open Building Institute webinar. This is on off-grid utility systems for the Seed Eco Home. So I'm going to hide myself here and continue going. So Open Building Institute is a collaboration between Open Source Ecology, Open Building Institute, building upon the hardware machines work of OSE with an application to off-grid sustainable housing, where the mission of Open Building Institute the mission of the Open Building Institute is to make affordable ecological housing widely accessible. So that's the name of the game here, using a modular construction system, building upon the machines of OSE and building upon other workshops. Like in 2015 we had a major build of the aquaponic greenhouse, and this is the result from 2016. We use a crowd-based collaborative method where a large team of people swarms on a build in parallel to accomplish pretty magnificent feats. Here, this is a house of about 1,300 square feet that was built in a period of 5 days, and the greenhouse here was built in another 5 days as well. Now, how do we do that? We first come up with a plan. This is our very basic Seed Eco Home concept with all the different utilities that exist on the Seed Eco Home. So starting with 3,000 watts of PV panels, we have a pellet burning stove, a thermoelectric generator. As part of the utilities, we catch water from the roof and from a catchment surface pond. We have a water cistern. We have a biodigester that takes the household organic waste and converts it to biogas for cooking. We also have hydronic heating subfloor that's provided by the hydronic stove, which means the water is the heat exchange medium that heats the house. Rainwater catchment here. We've got super efficient utilities like a super efficient fridge, which is a top-loading freezer to refrigerator conversion, and some other features. So that's the concept, and this is more of the concept. This is the overhead view of what you've seen in this picture here. The floor plan is like this. So how do we do the water, electricity, and other utilities? Let's start with the water. So the way we're approaching the utility systems are pretty much putting all the utilities, except of course the PV, which is on the roof, into the utility room. So all our water, biodigester, waste systems are kind of pumping through there, and it's centrally located so it can feed the kitchen and bath. As you see, the water utilities are pretty much centered around one side of the house, where because the kitchen is there, it's close to the utility room, so we're not running pipes or electricity all over the place. A lot of that is centered around one side of the house. So we have a 3,600 gallon tilapia pond, which you might have seen in some of the previous webinars. We have a 30,000 gallon surface pond that provides the water. We have rainwater catchment from the roof. So the sources here are one water line going into the cistern in the utility room, followed by rainwater purification and surface water purification to potable, up to actually an ozonator, which is the last step of the system. The bathroom wastes and the kitchen wastes go to a biodigester, which is right here, which then creates gas for the cooking, and the effluent, the fertilizer from that, goes into a gray water drain. And we're actually also collecting urine, and grain water effluent soaks back into the ground. That's the basic system. The biodigester bag is actually outside of the utility room, and as you can imagine, for the risks of explosion, if there's any leak, that gas safely leaks to not in the house but outside the house, so that's a safety feature right there. So let's start with the water. The rooftop catches 800 gallons, because of all the surface area that we have, per inch of rainfall. So that's not bad. And then we have the 30,000 gallon pond, water from the pond. They both go into our utility room, which is back there. Now if we talk about the roof water, we have two long gutters, and they go through a first flush filter. It's a rainwater diverter, which flushes the first part of the dirty water, like all the dust and bugs, whatever you have, that gets trapped. It's simply a chamber that gets closed off once it gets filled up, and the rest of the water goes where it should, to the utility room. So here's the beginning of the big water system storage, like for example, if it doesn't rain for a month or so, we have a 30,000 gallon pit here. This is after the excavation. This took 1 day to excavate a pond that's about 30,000 gallons, and we're looking actually from within that pond right now. And it took another day to dig all the trenches, the wastewater trench, the water feed line to the house. And now this is what it looks like after a minor rain. This is in the middle of winter here. We have, you can see the power lines that are used for the 2 pumps that are in the pond, where a lot of the pumping in the pond is going to be solar, with also electricity from our grid if needed. And there's 2 lines. One is a thinner line for the cistern, and another one is for the freeze-proof hydrant. We have a freeze-proof hydrant, which is simply a hydrant that you can use in a winter. It doesn't freeze. It's below the frost line. It has a little weep hole at the bottom where after you turn it off, the water drains down so it doesn't freeze in the middle of the freezes of winter here. That's the installation right in front of the greenhouse. Here's a little bit about the diverter. You need about 10 to 50 gallons per 1,000 square feet of roof area. The way it works is the dirty water comes into the chamber. It lifts a ball that then closes the chamber hole, and then the clean water keeps flowing into your clean water container. We thought about using an 8-inch PVC pipe. We're looking at exactly that. It turns out 8-inch is quite effective. 18 gallons per 7-foot section, so we're going to get a 20-foot section and actually bend it around. Either that or 6-inch PVC, depending on the cost. It turns out that either 8-inch or 6-inch is quite affordable to do this. If we want to get, we will trap about, what is it, like 30 or 50 gallons, which makes that 10 to 50 gallon measure per 1,000 square feet. At minimum, like 12, our minimum would be 12 gallons from the surface area of the roof here. So 6-inch PVC pipe can get you to do that. So then you go to the utility room. That's once again in the overhead here. This utility room looks like this. That's the compressed earth block floor, sealed with some stone sealer. I was hoping for a better shine. We're actually going to put stone sealer epoxy on this, so it's actually a very shiny, nice floor that's long life, and you can clean it off very easily. But these are the cisterns. The rainwater cistern is here on the left. 2 totes, IBC totes, 275 gallons each. So about 2 cubic meters storage of water, about 500 gallons or so, or about 2,000 liters. And then 4 cisterns for the biodigester. So the idea here is the biodigester is inside because the biodigester needs warmth in the winter. It needs to be 95 or 100 degrees Fahrenheit for optimal efficiency. So that's inside. We're trying to build a system that's practical for an average home, or your so-called eco home, that can be replicated widely around the world. IBC totes allow you to do that. Putting it on the inside allows you to address the freezing temperatures in the winter, which is one of the main reasons why biodigesters may not be so popular in the temperate zone as much as in the tropics. So let's talk about the drainage. So after you've got water usage from the sink, bathroom, kitchen, you have overflow to this gray water drain, long pit, and this is what it looks like right after digging, which is then backfilled with gravel, about 14 tons of gravel. But the idea here is we've got a 3-inch pipe for gray water and biodigester effluent, so that's essentially fertilizer, with a clean out, so that's 3-inch, and then draining into perforated 6-inch drainage pipe, which has got holes, and that leaches out over 75 feet of this 3-foot wide trench. Now we're also collecting gold water here, so that's actually our urine collection system, where we have a 55-gallon drum, a pipe from the separating toilet in the bathroom, and that is still being installed. We're working on that, so that you can store all this fertilizer for agricultural use. What you would do is pump it out with a pump sprayer, system and go around the fields, like for example our polyculture of hazelnuts and chestnuts, that would be perfect fertilizer for us for various agricultural operations. First in the world, people. You heard it here first. We don't know if anybody else was doing that in a so-called kind of an actual real utility that's installed into the home. It's going to be mainstreamed in a few years. Just kidding. Okay, drainage pit. This is what it looks like. It's got tar paper over the top of it so that the soil does not clog up the holes within the gravel. This is after the gravel has been spread, and now it's ready for backfilling again with the bobcat there, buried 1 feet deep. 14 tons of gravel in there, so a lot of gravel for a long distance downhill. Next is the water system. So we're using an earthship style filter, which essentially has an on-demand pump. In our system, we're going through several steps of filtration and then to a pressure tank, so that this pump only runs a few times a day to fill up a 44-gallon pressure tank, which then gives us a flood of water. Like the pressure tank, the good thing about a pressure tank is while this pump can be very tiny, and in fact right now we're using a 1 gallon per minute pump, which would be really insufficient for a lot of household water use, well, we're using a pressure tank such that you can have a real powerful spigot coming out of that as water gets pressurized in this 44-gallon pressurized water tank. Now the steps here in a typical earthship style filter include a 500 mesh filter, which is a settling filter. Basically you collect the debris and drain it once in a while, followed by a 1000 mesh filter, followed by one of the last steps. There is a ceramic filter which filters down to 1 micron, which gets you a lot of the microbes and bacteria filtered out. But we have a step after that, which is an ozonator, actually. So after we get the ceramic go through the ceramic filter, we go through an ozonator, and we have a little design of an open source ozonator right here that I'll talk about. Before going into this earthship style filter, we have a sand filter, which if we're pumping from the pond itself, we settle out a lot of the solids here. It's the general word on sand filters is that gets you down to 20 to 100 microns in terms of mesh size. Now I've also been looking at some of this. They say that zeolite sand, so other filter media, more fine sand or more high performance sand, gets you down to 5 micron, or glass. So read about glass sand filters, and which can go down to as little as 3 microns. So we're going to explore with this how pure do we have the water after the sand filter, which is a good idea because it's actually back flushable. It never clogs up. You can back flush it so that the sand filter medium in there is used for life. So we like that from a lifetime design perspective. Now here we have this is the actual parts that we bought. So we actually bought these, and this document will be online. You can download this document and you can actually click on the links here. If you see that, there's a link there that takes you, for example, to the source of that Sandmaster soft-sided above-ground pooled sand filter system, etc. So all these parts are hyperlinked. So the first filter is a 500 mesh, 27 micron. The next one that we're using is a 1000 mesh, or 13 microns. We're also using a couple more. There's a carbon filter in the system and a ceramic filter at the end. These are, what are these? If you click on them, they're carbon block filters to get you a lot of the chemicals and smells out of the water. We're looking at using 2 of those, and more and more. So this is basically, we're making a modular filter assembly where we can add more filters as we like depending on the purity of the water, because we're really experimenting here. All of our work is experimental to push the limits, and if we find that the system doesn't work, we can hack it. We can perhaps add another sand filter. One thing I was thinking about is maybe we could have another large, this one is about 5 gallon volume or so, add another one with charcoal medium, activated charcoal medium, to get you further purification. So we're going to explore which really works so that we can get to the final step, which is ozonation. So you can do yourself buy yourself a very low-cost ozonator system. You can get one for under $100. You can make one yourself even easier. It's this ozonator here, this little device here. You see my finger there. that's a high voltage discharge in air, which basically creates ozone, and gas flowing through one inlet and out the other picks up the ozone, and that goes into the water. So what you do is get yourself a $14 air pump, pump that air through the ozonator, and then go through a check valve into your clear PVC in your water system to feed that gas into the water. And the check valve is used so that you don't have water back feeding into the ozonator, which would short circuit that, it would fry it. So let's talk about next so we talked about purification. Let's talk about biodigesters, now some of the waste system. We're picking up on the Solar Cities biogas digester, which is one of the popular ones out there. There's definitely critiques of it. We're trying to basically take what we think works and what doesn't, and modify our system to do this. But the promise is actually quite grand, in a sense that 10 liters of mixed organic waste can get you up to 1,000 liters per 24 hours of time in 1 cubic meter of space. In other words, one of the IBC totes, the international shipping, those containers, they produce their own volume in gas if you let them, if you have ideal conditions of the right temperature and right feedstocks. So that's what we're aiming for. Now 1,000 liters gets you 2 to 5 hours of cooking time per day. Now that's enough for a family. Or you can even run a 1 kilowatt generator for 1 hour per day. Now that's pretty outstanding. So it will pay back if we can get this system to work out. Now that's a theoretical optimum from a 1 cubic meter system. Now we have a 4 cubic meter system because we want to be robust and resilient, and build the system modularly, so if one part fails we can use another container and so forth. So our basic concept design for the biodigester. Now, unlike the Solar Cities, we are after absolute automation. So that means you flush the toilet, you run the incinerator or macerator pump under the sink. What we're using is macerator lift pumps under the sink and under the toilet that then feed that's the inlet, that's what feeds the digester through a check valve, so you don't have backup. That goes inside the digester. Inside the digester we have a little pump. It's basically a trash pump, an agitation pump, which pumps through the system in a circle and agitates the solids and liquids within there. You also need heat, and this is where our hydronic stove comes in. So having hydronics and 1/2 inch PEX tubing, we're sending that into the digester to heat the system, with the goal of keeping it at 90 degrees or 100 degrees all year round. We're going to insulate the totes also, so around these totes we'll put styrofoam insulation to keep the heat in, and so forth. This is the basic diagram. There's a gas outlet to the gas bag. So I mentioned about the gas bag. I'll go back here. The gas bag looks like this. That's the actual picture of that. It's a big 3 cubic meter scum bag. It has a fitting with a barb on it for inlet, and after the digester. So the biodigester is right here in this diagram. We go through a hydrogen sulfide scrubber, which is a household filter filled with steel wool that will degrade in the presence of hydrogen sulfide. So some hydrogen sulfide will be produced in a robust system. If you're feeding that system everything, you're going to need to clean some of the hydrogen sulfide, which is a foul-smelling gas that corrodes metal. So you want to get rid of that. It's also, but however, it's you might not want to get rid of all of that because it provides a smell, so that you know when the gas is on in the house, or if you have a leak. Just like in regular gas appliances, they add an odor to the gas. The gas is pretty odorless. They actually add an odor to the gas, so you smell when there's a gas leak. So we have that by default here. So we're going through some clear vinyl tubing into the digester bag, and the digester bag will be in a treated 2x4 wood frame with 1/4 inch hardware cloth around that, so that you don't get rodents chewing up your gas bag. We're going to put a weight, such as a 2x12 or something, or piece of lumber on top of the gas bag to provide the pressure to empty the bag once gas is produced in there. So that gas then goes back through the system. Before you go to the stove in the house, we'll go through another steel wool filter for hydrogen scrubbing. And we're also going to put in a clear vinyl manometer tube, basically to show the pressure, manometer tube that shows the pressure that you have. So in this system, because we have heating, we've got automatic feed every time the toilet or the sink is flushed. We have automatic agitation, pretty much automatic gas collection. This system runs by itself. The effluent, which is actually tapped not off from the top, actually a little bit below. You want to leave the top surface, which probably is going to have a lot of grease in it. You want to leave that intact, I believe, because grease, as far as the numbers, that's by far the highest producer of biogas. When grease decomposes, you get a very high percentage of biogas that comes off it. So you don't want to drain that into your gravel pit. You want to keep that in the biodigester until it basically turns to your gas and carbon dioxide. So we have a means to flush this system out by gravity, using the gravity, just turning the valves here, or by the pump. If we open the valve to the exit, this is an outlet for forced pump out, or by gravity. Okay, moving on here. So let's talk about the stove here. So after we go inside the house system will therefore contain a 100-pound propane tank and our digester bag. And as the progress of this goes, we hope to be running off the digester bag all the time, as opposed to our store-bought propane, to show that this actually works. We go through a 3-port diverting valve and into our appliance, which is just a regular appliance. You don't have to hack the appliance, you just need to connect to it. And here's a little more about the manometer, just an indicator for the amount of gas pressure that you have. So let's move on to the hot water system, which is based around the hydronic stove with heat exchanger. So the heat exchanger is this. So this is a picture of our stove. In it you have a pipe-based heat exchanger. The heart of the system is the hydronic stove, 1-inch pipe heat exchanger with water inlet and outlet. So cold water comes in one side and hot water leaves out the other after it meanders through the heat box in a hot flame. So this is our open source hydronic stove, about $500 in materials including the heat exchanger. So that's ridiculously low cost, especially because the nearest competitor will cost about $5,000 for a water jacketed stove. In our stove we have a nice seal gasket around, so you keep the smoke out. It's a modular design where the heat exchanger is actually a separate part on top of the burn chamber, and the bottom piece, the ashtray, is actually a separate component as well. So that's the heart of the heating system, all open source and connected to the open source hydronic control panel. Now this stove, what's unique about it is actually a dual fuel stove, meaning that you can add either a regular fan or a pellet burner module to it. So here's our DIY pellet burner, essentially a double tube where air is blown from behind. This is not assembled or completed, but this blower fan will be blowing from behind this. Pellets will be going down this chute, ending up in this fire chamber, and air will be coming in through that annular surface in between the two pipes. So air will be coming from the bottom through these little holes. And this is the grate, and either we run on wood or we just lumber, just firewood, or we attach this pellet burner, which can be controlled automatically for on-demand operation or automatic operation. Now then we connect to the open source hydronic panel. If you Google that, we are known for developing this. It's a basic system, but what we have is an actually fully documented version with all the bill of materials. You can see the documentation on the wiki. We've started with this kind of a system, and then actually simplified it in the next iteration because we didn't need some of the parts. Like, for example, because we're not using a big water jacket on a stove, we're just using half-inch tubing throughout, we find that if you do some calculations, you see that the tubing expands a little bit, and it's just enough to meet the thermal expansion of water. So you don't need a pressure expansion tank. We also, instead of air purge valve, we have a very simple on-off valve, and instead of this a mixing valve here, all of these which components cost about $100 each, we're eliminating that. You can see the details on the wiki. The water from the stove comes in here and there. This is our 2014 version. This is the hydronic control panel from 2014. This is what we did in 2015, and we're building up a version much similar to this for this year with a very basic system. So going back to the overview of the hot water system, there's a couple of nice treats in there as well. We're going to put also a hot water heater, a simple heater just like everybody uses, fueled by gas or electricity. We're just going to put that on top of the stove, so we don't have to use electricity or gas to heat it. We're just going to get the heat from the stove, and that will get you hot water in the winter. But also we have an on-demand water heater, which in the winter we won't have to use because we have hot water from the hot water heater on a stove. But in the summer, if the stove is off, we would use the on-demand heater here, and then eventually develop our own open source on-demand heater, which would run on charcoal, which is a very robust fuel. So from the hot water heater, we go to the hot hydronic control panel. We go to one of the avenues for the hydronic system is the biodigester heating, and the rest goes to the house heating system. So two major parts: the household under the floor hydronic heating, which is I'll show later, or the biodigester, like I talked about, which needs to be kept at a high temperature. So we have the water pressure tank, the 44-gallon entity that I talked about before, that goes to feed the water in the house at pressure, or it goes into the heat exchanger, which is getting you water, the cold water that goes into the feed water into the heat exchanger. If that gets used, one part of the system you get feed water into the heat exchanger, which is that water that goes into the floor is not the same water that goes to your hot water faucet. Those are two separate systems. Here it's drawn a little bit inaccurately, but the idea is that the heat exchanger water, you want to not be putting oxygenated water into the heat exchanger, or it will rot out your pipes after some time. So what you want to do is have that as a closed system, so that oxidation of the metal pipes is minimized. That's why typically people don't want to have a heat exchanger that's also feeding water to the house, because you'd constantly be getting water with oxygen. And the tubes under the floor, they're called actually oxygen barrier PEX, and that refers to the fact that they don't allow oxygen to go through those pipes. They also have other types of PEX pipes which do allow some oxygen to go through the walls of those pipes. Okay, now the very unique thing is that we also have a thermoelectric unit right on the heat exchanger. So on top of the stove we are laying a thermoelectric generator, I'll show that, which traps some of the excess heat from the stove and converts that into electricity, and that's heated convectively by water from the it's actually right on the stove. It's not even convection, it's laying right on the stove to get the hot side, but it has to be cooled on the other side to get a thermal gradient, and that's actually pond water that we're sending through that will actually, once it flows back into the pond, it gets warmed up a little bit. So we're doing multiple things there at once. So I talked about the hydronic control panel. This is the actual hydronic tubing as it was laid under the floor. And we're also using a hillbilly heater, what we call, which is basically solar gain inside the greenhouse. This system we are connecting to a heat exchanger, basically a blower fan and a radiator, like radiators in a car, which will blow hot water. Well, the water flows through the heat exchanger, the air fan blows air through the heat exchanger to heat up your house. Now, in the former version of the greenhouse, which is the 2014 build of the home, and the 15 build of the greenhouse, that there's issues definitely on moisture in the air because the greenhouse is very humid. So there's times during the year, like in the spring and fall, where the greenhouse is really humid and it humidifies your entire house. So you want to separate you don't want to be blowing that air directly into your house. It works quite well during dry times, like maybe the heat of the summer where you don't need the heat, or like the dead of winter where the air is relatively dry, or the air in the house is relatively dry, so moist air is actually useful. But in general, we want to isolate the greenhouse air from the house air so you don't get all kind of rot inside the house, because the greenhouse is very humid. So you do a heat exchanger system like here to make that happen. And here's the thermoelectric generator. So this is our prototype, and what's going to happen here, these two pipes, one is a cold pipe, one is a hot pipe. One pipe is going to rest on the stove, the other one will have cold water pumped through it from the pond, and there's thermoelectric little generator modules that produce electricity, and our goal is to produce 100 watts for nighttime power usage when the PV is not in operation. So the separating toilet is a mystery here. We still haven't installed it, but what we're doing for the separating toilet is, this is the actual pedestal for it. This is where the toilet is going to sit. But what we're doing is, it's very hard to find a separating toilet in the United States. It's a little more common in Europe. But in the United States, what we're doing is simply taking a stove and a diamond drill bit and poking a hole at the front of the toilet for the urine, and then the solid waste go down the back like normal. But we're hacking a regular toilet, and then 3D printing a urine catcher that will catch the urine that goes out through a little hole at the front of the toilet. So that's our idea for what we will do. That's currently in the works. Here we're seeing what the actual macerator lift pump looks like. So here's where the toilet sits. This is 3-inch pipe, like standard plumbing under a toilet. But instead of going down the drain, notice this is not going down further PVC. This is getting pumped out through a 1-inch outlet and goes up against gravity and into the biodigester system in the next room. So it's actively pumped from the toilet. And the same pump like this will be under the sink, macerating food waste from the sink. And we're sitting the toilet on a frame, on a pedestal. We're doing the same for the shower, such that these units, according to our modular build methods, can be built in parallel as we're turning these into modules as opposed to like monolithic built-in-place things. So that's part of our modular design, which allows a large crew of people to work in parallel. So next item is the super efficient refrigerator. That's we're proud of that. Thanks Dorkmo for doing this, but this is an open source design. It's fully documented. It comes from a project called Mount Best, and this is a replica of that. This is the Mount Best freezer to a refrigerator conversion. All you're doing is you're taking a regular chest freezer, which has a really well insulated body, as well as the door opens up so that whenever you open it, all the cold doesn't leak out. So using this kind of a system, where what you're doing is instead of letting the freezer run the whole time, you just time the pump in there, the compressor, the freezing compressor there. You cycle it on and off so that it's on only a part of the time. Therefore, it retains a temperature not freezing but above freezing, which is done by a little controller. So that's a little Arduino in here, a little brain that measures the temperature inside the freezer, and when it gets to keep it within a certain temperature range. So there's a probe that goes into the freezer inside the body of the chest freezer to measure the temperature. Very nice, elegant system. Like this whole thing and the parts, including the Arduino, you can build for under $50. So it's really excellent, and you can solder that by hand. So actually we've got the plans for this. We encourage you to copy that. It works excellent. And the idea is, now you're turning the power from an average of 100 watts consumption for an average refrigerator to about 8 watts average power, 12 times less energy usage. That's a major savings, if you're ever considering going off the grid and living with a minimum energy budget, or trying to live from the solar collection during the day, because in principle, if you don't open this up at night, or you have a lot of say ice in there, or a lot of mass of, well, not ice, but mass, if that refrigerator is filled, it can probably keep its cool throughout the whole night, so you might not even need to run it at all during the night. So yeah, maybe a little more about the utility system. Well, is this part of our utilities? Well, it feeds us. That's the aquaponic greenhouse from the 2014, 2015 build. That's the 2015 build. The food is what feeds us and then goes into the digester and so forth. So this is going to convert some into gas. It's part of our utilities and also food for the humans. This is actual pictures of the hydronic control panel. Control panel for aquaponics. There's going to be another webinar coming up next month about the whole automation of the house, including how we're watering all the plants, how we're making all the systems here work together off of the grid, automated. Like, we don't want to be messing with the watering sequence for the greenhouse. We want our hydronic stove to turn on automatically and everything to be automatic, so that this is a system that runs by itself as opposed to requiring a lot of maintenance. So here, let's take you to the open source PV system. That'll be source PV system. As I haven't covered the PV system yet. That's one of the last things here. So if you look at the page on the wiki, open source PV system, we installed 3,000 watts of power. That was during the install. We mounted the frames on individual rails, like you see here, with little angle brackets welded to angle frame. So each of these panels had these metal frames attached to them. And then, see, we built all of that in the workshop, and then we simply carried all the panels up there and just screwed them into those 4 wood beams. They're cedar beams on the roof. So we did all the well, not the wiring, but some wiring and the framing of the panels, which come with this aluminum frame. We put the structural frame around them so that we can simply attach them on the roof. So that was very much turnkey. And as far as the PV panel, we have run off-grid power tools on that already. It works great. We're minimizing. The way we're designing this is that we're using only. So if we go into maybe this document, I can show some of the system. I mean, the system consists of your PV panels. You've got a charge controller, which is a maximum power point tracking charge controller. That's in there. We actually have 3 of those. We have a regular breaker box that operates from after you charge. We have batteries in here, simply 8 motorcycle batteries. That's really minimal. It's about $160 worth of batteries. Not a lot. They are we convert DC current to AC, so we run the AC through a regular outlet, basically a breaker box that feeds the rest of the house through breakers. But we're also designing this such that we are able to tap 120 volts directly off the panels, that we're able to tap 24 volts directly off the batteries, or 20 volts off the panels. So a multiple voltage DC system plus your AC of 120 and 240. And the idea is we're running a lot of the loads, whatever we can, on DC, because if you go through the charge, discharge, inversion cycle, you're down to 60 or 70% of the energy you had from the solar panels. So whenever possible, we want to avoid that and run loads during the day, like for example pumping the entire water storage system during the day, as many loads, all the pumps and the aquaponics, fans, anything possible during the day, so that we shut everything off at nighttime as much as possible. But the figure that we're working with is how much energy do you really need to survive and thrive? Well, what do we use? Let's see, do I have a calculation here? I'll tell you about that, but I just want to tell you one more thing here, that these PV panels, they cost, let's see, there's a cost graph here. So here I show everything about a standard racking system would actually, the point about a standard racking system, so we just hacked it by using lumber on top of the roof, which was very easy to do, but the professional way to do that is more than doubles the cost of the PV itself. These racks, the professional uni racks, they would be about $1,600 plus shipping, whereas the solar panels themselves, they were about $1,840. So a pack of 12 of these solar panels, about 280 watts each, cost us $1,840. We did this low cost racking system as I'm describing here. You can look up all the details on the wiki with what we did for the fasteners and washers. The whole plan is here. Now let's talk about the loads. Look at this, very inexpensive. So 1,840 plus the control panel, you get yourself 3,000 watts of off-grid power. And also such that, the inverters are extremely affordable right now. You can get split phase 240, 120 inverters for like $500 or $400 for like 8 kilowatts, which is amazing. So actually what we're doing is getting one of those inverters, and so that when we do future builds around the Seed Eco Home, because we're going to add to it, create workshops around it, we can do things like actually run full powered MIG welders and big air compressors for power tools right off our teeny little battery bank during the daytime when the sun is shining, because we can be trapping all of that energy almost directly from the panels, but we're not running directly. You actually have to go through the batteries in a standard way that a standard electrical PV system works. It's kind of backwards in the sense that very few tools or like the system does not lend itself well to using direct loads coming off the PV panels. Typically the systems are designed to go through the charge cycle and through batteries, through inverters. But nonetheless, we're trying to hack it how we can have as many loads go directly from the panels, essentially by having a large number of multiple loads, connecting one or two of them each per panel. So that's why we have this very funky, if you looked at some of the diagrams or this one here, we've got a very funky control panel where we've got switches and takeoffs for power. Like, we're really hacking it in terms of access to maximum hacking on that panel. Like if you look at some of these diagrams, here I'm just working out how you would this is not completed yet, but working out how you have terminal blocks and bus bars and everything, so you can tap all the loads in a very, very flexible way, so you can optimize this system for the efficiency of running mostly throughout the day without going through the charging discharging cycle of batteries going directly from the PV panels. Now, to do that, we have to understand our loads very much. So we've got a collaboration with Michigan Tech University. There's a fellow grad student who's actually doing an open source power meter which measures the voltage and current, in other words power, at all the different loads that we have here. So we're actually going to install that. That's currently work in progress. We're going to install that right on our control panel so that we know exactly when the power comes in, when it cuts out, like when the batteries, when the PV panels start producing power during the day. So we're going to log that and graph it so we understand our load usage exactly. Therefore, we can optimize this and provide a very low-cost system that's designed for flexibility. So that's that. Well, that pretty much wraps up where we are right now on the Seed Eco Home off-grid utilities. We have number 9 more webinars after this one, so stay tuned. But yeah, we were very proud of this build, and we look forward to the next. If you're interested in finding out more about this, we're at the end of October of 2017. We are going to run the second iteration of this Seed Eco Home. So right now we're finishing all the utilities, documenting everything. Of course, it's taking a long time. A lot of highly experimental systems. We're going to report on the full automation of the greenhouse and house next month. But yeah, we're going to do this again. Basically take all the learnings from here, build on the structural learnings, and then build on the utility learnings. The utility learnings are huge this time because there's things we've never tried before, like the biodigester or the thermoelectric generator or the pellet stove. I mean, a lot of very cool features in here that we're doing. So yeah, stay tuned. Thanks for paying attention to this. Please write your comments below the video once this is released, and we look forward to more builds and bringing world-class education or world-class hacking of the existing systems directly to you. Okay, thanks a lot. Take care.